For the first few 100 million years of its existence, the young universe was entirely devoid of light. This was a cosmos without the glow of a single star or the reflection of a single planet. This early era consisted of an expanding, cooling ocean of simple hydrogen gas. No galaxies yet existed to illuminate the matter, and no stars had yet formed to pierce the blackness. Scientists call this the cosmic dark age, a multi-million-year period of quiet preparation, where the laws of physics began the slow work of organizing the vacuum. This visualization shows gravity acting as the primary sculptor. It identified microscopic variations in the density of the hydrogen gas, pulling these particles together to create the first pockets of mass. As these regions gained mass, their gravitational pull increased exponentially. They dragged in more hydrogen, forcing the gas to collapse inward until the internal pressure and temperature reached extreme levels. Darkness was the mandatory starting point. Without this long, patient gathering of gas, the universe would never have reached the densities required to create light. Eventually, the pressure became so great that it forced hydrogen atoms to fuse together. This was the moment of fusion ignition, a sudden, violent eruption of white-hot energy deep inside the matter itself. This reaction served as the universe's turning point, transitioning the cosmos from a state of Coulomb gas into a state of active, sustained brilliance. These first stars were enormous compared to our sun. They burned with a violent intensity and lived short, turbulent lives before exhausting their fuel. In the absolute blackness of the Dark Age, these stars turned on like isolated torches, creating their first independent pockets of glow in the void. The appearance of these stars replaced the chaotic, uniform ocean of gas with a structured cosmic architecture. For the first time, the universe had a defined center and a source of energy. While gravity pulls inward, stellar radiation pulls outward, creating the equilibrium needed to form a stable, spinning disk. This radiation also triggered ionization, burning away the opaque hydrogen fog that filled the universe, making space transparent and allowing light to travel freely. When these massive stars ran out of nuclear fuel, they collapsed and detonated in colossal supernovae, sending violent shockwaves through the surrounding space. Inside these explosions, the simple hydrogen was forged into heavier elements like carbon, oxygen, and iron. These building blocks were scattered across the universe, seeding the clouds of gas for the next generation. Without the violent deaths of these first stars, the complex chemistry required for planets and life could not exist. Light destroyed the simple universe to build the foundations for everything that followed. Over billions of years, the elements scattered by the first supernovae clumped together once more. They formed second-generation stars and the first rocky planetary disks. These elements connect the early universe directly to our own bodies. The calcium in your bones and the iron in your blood were forged in ancient stellar furnaces. Because light takes time to travel, the photons from those first stars are still moving through space today. When we use our most powerful telescopes, we are looking directly into the history of our own creation. This chain of events led from the first heavy elements to the cooling of rocky planets, where complex chemistry eventually organized into self-replicating biological life. As biological complexity increased, it developed the capacity for consciousness, resulting in a species capable of measuring the very light that made its existence possible. The ignition of the first stars provided both the material for our bodies and the light for our eyes. Through us, the universe has moved from total darkness to a state where it can finally observe and understand its own existence.